Alright, so let's go ahead and get started with the Exam 1 topic of electron configuration. My name is Gant Meredith, and we're going to go ahead and jump into the material. So what is electron configuration? Well, electron configuration has to do with the orbitals present in an element, or in a compound. So, what I mean by orbitals is if we look at our periodic table, over here on the left we have this grouping over here. This is known as the s orbital. How do we know it's the s orbital? Well, let's look at our atomic energy levels in our orbitals over here. Each one of these lines represents a potential orbital that electrons can fill. Electrons fill these orbitals in a positive and a negative spin, and this is normally notated by an upward arrow like this and a downward arrow like this. This would signify 2 electrons in the 1s orbital. Now I say 1s orbital, where does the 1 come from? The 1 comes from n, which is the principal quantum number, and that has to do with energy. So it's the energy present in the 1s orbital. Does that make sense? So we have the s, which is this left side of the periodic table here. There's each element. When you go up from lithium to beryllium, the difference between them is that beryllium has 1 more electron and also 1 more proton than lithium. So with that being said, we have now established what the s orbital is, and we see that there are 2 electrons in the s orbital. We'll come back to this middle portion, but now let's go over to the right side. Here we have the p orbital. And the p orbital has how many electrons? Well, we can count. There's 1, 2, 3, 4, 5, 6. So the p orbital has 6 electrons, and that makes sense because if we go over to the left-hand side where we have our atomic energy levels represented with the orbitals, we now have 1, 2, 3 lines for p, which means that there are 3 p orbitals. They look like peanuts actually, oriented in the x, y, and z directions, and just like the s orbital, they have positive and negative spins. Now when it comes to determining the orbitals and what electrons are present in them, we do have a principle that we use to determine how we fill. We call it filling these subshells. So you see down here there are 2, there's a positive and negative spin, so there wasn't really much of an issue. So if we jump up to this orbital, we can do the same thing. But once we get to the p, d, and f, we have to fill each orbital partially first. And then after doing that, we can go back and fill in the rest of the orbital. But we'll get into that later. That's the S and that's the P. We'll come back to the middle. This is the D. If you count the D, you realize that there are 10 electrons, and that makes sense because there are 5 orbitals present over here on the left-hand side of the diagram. Now the F is where it gets confusing, and for at least organic chemistry and in materials, I have yet to see an example where the F comes into play, but it's worth mentioning. So the F we have down here. There are, if you count the number of orbitals, there are 1, 2, 3, 4, 5, 6, 7 orbitals, which means there are 14 electrons present in the F subshell. However, if we count the number of electrons down here in they're called the lanthanide and the actinide series, we count 15. Well, that's because the first elements, 57 and 89, lanthanum and actinum, are considered part of the D subshell. But again, this is just worth mentioning so you know, but we will not be encountering any of these examples for today's lesson. Alright, so what we are going to get into in a minute is electron configuration, but we'll also be going to getting into noble gas configuration. Essentially, noble gas configuration is just a shorthand way of writing the electron configurations. Before we get into further examples, let's walk through one. Let's look at the compound phosphorus, for example. So electron configuration, we're just determining what electrons are present in phosphorus. So let's go over here. We look at the principal quantum number 1, which means that we're in the 1 orbital. There is only 1 type of subshell in the orbital, or in the 1 orbital, and that is the s. So we will go ahead and write 1s, and how many electrons are present? Well, 1, 2. We have not reached phosphorus yet when it comes to counting the electrons, so we continue onwards. We now see that we moved all the way over across the periodic table to helium, and now we're going to go back over to the new energy level, the 2 energy level. We are now in the 2s orbital, so we'll go ahead and write that over here. And how many electrons do we have? Well, we can go all the way through the 2s orbital and not reach phosphorus yet, so we have 2 electrons present. Now let's come back over to the right side. We have now started to enter the p orbitals. If you look to your left, you'll see that there is a 2, so we're in the 2nd energy level of the p orbital. And as you can see, we do not reach phosphorus when we move all the way across the p orbital, so we have 6 electrons present in our p orbital. Jumping back over to the left side again, we are in the 3s and we do not hit phosphorus. So we're going to write 3s2, and then we jump over to the 3p orbital. Now when we look at the 3p orbital, we see that we get 2 phosphorus. So we are not going to write 3p6. That would be incorrect. How many electrons do we have? We have 1, 2, 3. 3p3. This would be the electron configuration of phosphorus. Now if we were to do a noble gas, well, what are our noble gases? They're this series right here on the right, this column. What is the noble gas that we complete on our way to phosphorus? Well, we actually cross neon. So what we're allowed to do, and this saves us a bunch of time, is to write the noble gas here, neon. And then we continue on our notation. So we do 3s2, 3p3. This is just a way to save time, but honestly, for starters, I would recommend writing out the entire electron configuration, because on the exam you can always save time by going back and writing the noble gas configuration. I would like to talk about the filling principle I was discussing earlier. So if we have our 3p orbital, we have the 3p x, we have the 3py, and we have the 3pz. And if you imagine a coordinate system in 3 dimensions, you would have x, y, and z. And each of these orbitals look like little peanuts, and they're all oriented in each orientation, the x, the y, and the z axis. And so when we fill the p subshell, we do so, we can call these positive spins, they could be negative, it doesn't matter, as long as we know that we put in 1 electron in each shell. We cannot put another electron here before we fill up all 3, because this is considered the most stable configuration for phosphorus. Alright, so let's move on to some examples. Now these are stable examples, meaning that these are neutral compounds. They're not cations or anions, they're just neutral. So we will get into ionic, or not ionic, but ions in the second round of examples. So let's look at rubidium. So this element, as you can see, is right here. So it is in the 5s orbital. So to get there, we're going to go through the 1s2, the 2s2, then the 2p6, then the 3s2, then the 3p6, the 4s2, but this is our first time dealing with the d orbital. Now the d orbitals actually jump down in energy level. So this right here would be the 3d. So we jump down 1 energy level when we go from the p to the d. But it's not too confusing once you remember that. So we have 4s2, 3d, how many? Well, there's 10. You can count if you need to. Or you can remember that the d orbitals have 5 areas that we can fill electrons. And remember, you have to fill electrons 1 at a time. Alright, so we have 3d, 10. Then we have 4p6. So even though the 3d jumped down 1, we still go back up to the correct number for the p subshell. So 4p6 and then 5s1. That is how we solve rubidium. Now let's look at Rhodium. Rhodium, as you can see, is inside the D subshell, so we get to go into this subshell. Let's try the noble gas configuration, for example. Because we've already solved rubidium, we know that the last noble gas that rhodium passes through is krypton. So if we wanted to write out the noble gas configuration, we could start with krypton, then do 5s2, and then 3d, or 4d, excuse me. 1, 2, 3, 4, 5, 6, 7. So 4d7. Let's now look at zinc. Zinc is the last element in the 3d subshell. So, using noble gas configuration to save time, we can start with argon and then do 4s2, 3d10. Alright? Now let's do chromium. So chromium, as you can see, is the fourth element in the 3d subshell. So using noble gas configuration, we should be able to do argon, 4s2, 3d4. But unfortunately, you cannot do that. This is one of the exceptions to the noble gas configuration rules, or to the electron configuration rules that we have already learned. If we look at chromium, let's look at the 4s and the 3d. So if we fill the 4s2 first, it would look like this, and then we have 1, 2, 3, 4. So let's go ahead and add those over here. 1, 2, 3, 4. Excuse me, I realized that I only wrote 3, that would be for the P, but we need 5 different orbitals for the D subshell. So you can see that we have 4 present in the D. Now, earlier we said that if we put 1 electron in each of the orbitals, then the compound would be stable. Now, if you think about a D orbital, there are multiple ways to draw one, but D orbitals are even greater than a P orbital. So an example of a D orbital would be like this. Now, if you had this huge concentration of electrons, wouldn't you want this to be happier than the small little s subshell right here? You would. So what we can actually do is borrow one of the electrons from over here and move it into the D. So now we'll have 3d5, 4s1. And this is again because we want the 3d subshell to be stable. And the 3d subshell needs it wants to be much more stable than the 4s does. The 4s is the s orbital in general is very small, and it doesn't necessarily need to be that stable. But the 3d does, because you have 5 different areas of electron interaction. Does that make sense? On the next slide, you'll see the answers if you want to check yourself or go back and do these on your own. And now we'll get into some of the ion examples. So if we think about an ion, let's think about a positive charge. A positive charge means that we lost electrons. So if we look at our periodic table and think about a continuum from left to right, positives would be moving left because we're losing electrons. And then negatives would be moving right because we are gaining electrons and getting closer to the noble gases. So if we look at aluminum 3+, we go to aluminum on our periodic table, which is right here. Now, if we do the electron configuration, it would be neon 3s2, 4s1. We'll go ahead and write that out. Excuse me, that should be a 3. 3s2, 3p1. Now when we remove electrons, we want to remove them from the highest level, or highest energy level first. But we have 2, 3 energy levels, so it doesn't matter which one we would take one from first, but you should start with the p because those are the electrons that are least shielded, because they are the most outward of all the electrons. So we will remove 1, 2, 3 electrons from aluminum because it's aluminum 3+, and that will actually give us neon. So neon is where we get, and so neon again is 1s2, 2s2, 2p6. So that is what Al3 plus would be. Let's look at scandium plus. Now, scandium is right here in the 3d1 position. So I just finished saying that we remove electrons from the highest energy level first. So when I say the highest energy level first, I mean we're going to remove them from the 4s before we remove them from the 3d. So we remove one electron here in where the calcium position would be, and then we get the noble gas argon, and we get 3d1 4s1. Now notice that I put the 3d in front of the 4s. It's honestly just a convention. You could put 4s1, 3d1, it does not matter. I just prefer to put the smaller number first. It just is more aesthetically pleasing. Okay, let's look at zinc now. So zinc is all the way at the end of the 3d subshell. So zinc plus would mean removing one electron from the 3d. Now, I just said that you want to remove electrons from the remove electrons from the highest energy level, which is true. So this example is interesting because we have the 4s2 that we would remove from, and so we would actually only be left with 4s1, 3d10. Now, this zinc plus, I actually looked it up online, and it's not a real element technically. But the point of this example was to realize that you would draw from the highest energy level first, but let's imagine that we were somehow getting to copper. So if we had copper as our example instead, just neutral copper, there's a principle similar to the one we did with the neutral examples, where with copper, because it is a 3d9 orbital, it would want to be more stable. Let me draw out the D's really quick. 1, 2, 3, 4, 5, 6, 7, 8, 9. And we don't forget that we still have the s orbital that has 2 electrons. So, just like before, we'll take one from the s, move it over here to the d, because the d orbital needs to be more stable, or stability is a higher priority for the d orbital than it is the s. So now that we have done that, if we were to look at copper, copper would be the noble gas, and then we would have 4s1, and that's what I was trying to get at with the zinc plus example, but we still have to keep in mind the rules where we draw from the highest energy level first when we remove electrons. So let's do our final example, chlorine minus. Now if we look at chlorine, it is all the way over here in the 3p5 position, and minus means that we add electrons, which means we move to the right. So actually what we would get is argon. So argon is the 3p6 position. Now in order to check ourselves, I have the answers here, so you can go back and do them on your own time. Note that this example is technically incorrect because we were removed from the highest energy level first. Now, when we looked at chlorine, and we did chlorine minus when we got to argon, this concept is known as isoelectricity, or you could say that chlorine is isoelectric to argon. Iso means equal, And then electric has to do with the charge, plus or minus. So if we look at chlorine minus, we move 1 over and it's isoelectric to argon neutral. Now if we were to do selenium 2 minus, that would be isoelectric to krypton. And if we were to do calcium 2 plus, what would that be isoelectric to? Well, calcium 2 plus would be isoelectric to argon. So you could even say that calcium 2 plus is isoelectric to chlorine minus. Now that about wraps up most of the concepts for electron configuration that might be present on an exam, both in materials and chemistry courses, and I hope that this was informative. Thank you.